All right, so let's take a look at what happens when we add a flexural piece into a column or beam column. So we're still doing solid columns and bearing walls. The difference here is instead of just having, just draw an Euler buckling column. So we had just axial before. So now we're going to also add in some sort of lateral load, or it could be an offset load with an eccentricity, anything that causes a bending moment in this column. So the big difference being when I'm in pure axial, there's a critical point where I reach buckling. When I'm in axial and bending combined, I have to consider the two of them and how they interact. And certainly this type of load that forces you into bending is going to reduce your capacity. All right, so let's just talk about how this all comes together. Just briefly mention tension with bending. So it can be an axial tension. The place this comes into play might be on the bottom chord of a truss. If the bottom chord is loaded both at the kind of working as a flexural type member as well as the point loads from the individual tie-ins. So in this case, we've got what I just talked about, but you've got some kind of bending load and you've got some, and you've got an axial load, but it's in tension. So this is an interaction formula. If you can remember in concrete, there's an interaction formula for columns that looks something basically like this, where this is axial and moment. If you're in steel, you have another interaction formula. And if you haven't had either one of those classes, not a big deal. This is basically a straight line interaction diagram, so a basic interaction diagram where this would be, in this case, axial tension, and this would be, I'll just call it bending, but it's moment. And I go from, so less than or equal to 1. This means that if this tension piece is 1, I have nothing left for the bending piece. And if the bending piece is 1, I have nothing left for the tension piece. So I balance those two, and that total has to be less than 1. Okay. So in this case, the shaded area here is okay. If it falls outside of the shaded area, it would not have the capacity. Okay, so these are the basic formulas. I'm not going to do an example with this one. You aren't going to have to do this too much. A lot of the trusses you'll do, unless, yeah, a lot of the trusses you'll have on site are going to be delivered, as we talked about, as completed units. Okay, so this is all in section 3.9.1 of the NDS, and this lets you know what the different factors are. This one we've seen, we had something that looked a lot like some of these terms when we were looking at columns, but the lateral stability piece. But now we're going to obviously have the lateral piece due to the bending. All right, so F sub B star is the adjusted reference bending design without CL included. F star star or FB star star is everything except for the C sub V term included. All right. But let's talk about combined bending and axial in the case of compression. So if you go into the NDS, take a look at section 3.9.2. And instead of that straight line interaction diagram, I'm going to have a modified version. And this is because when I'm in compression, I've got that buckling piece, right? And so as I buckle and also have bending from the lateral force or the moment, the further I get away from the center line here, I get what's called a P delta effect. In other words, if this is P, it's away from the center, so it's getting further and further. That's what's called a second order effect. It's fairly complicated, but if we, the interaction diagram and the equation is set up to take into account some of that instead of just having pure linear interaction diagram. So what does this look like? In that section 3.9.2, we've got the formula for bending plus compression. So what do we have? We have axial here. Here we've got bending strong axis. And then here we've got bending and the weak axis, okay? In other words, the second term, we use subscript 1 for strong axis and subscript 2 for weak axis, and the first term is our what we already dealt with axial compression. Okay? And so we'll use these formulas. For a typical stud wall where we've only got the x-axis bending, you remember we talked about that in the columns, then we can actually get rid of the weak axis term and we get just the simplified version. Okay, so you knock off the weak axis term. Now, if I had a freestanding column that had axial load, it had lateral load, and then in and out of the paper, it also had a load kind of in the third direction. It could buckle both in and out of the paper as well as along buckle in plane. So that's certainly something to take care of. We're not going to look at that particular case because it's just more of the same. You're just going to add a second term in the weak axis. A lot of what you'll be doing if you're doing wood design are going to be these sheathed stud walls or braced in one direction. Okay. So when we do have a load in both directions, we have to deal with this. But in this case, we're looking at just strong axis bending for the stud wall case. All right. One other thing to just know here is while we don't have the big load factors on, like the 1.2 and 1.6 that we have in steel and concrete design, we do have load combinations that are still taking care of the fact that we can't have, that we're not likely to have dead live, max dead, max snow, or rain, or roof load all at the same time. And so you just remember that these load combinations exist. We've been basically doing problems with these, right? They don't have any factors on them. We start looking at lateral loads. That's going to be wind, earthquake, but we're not going to do earthquake because that's a special case. So 3, 5, and 6, 3 controls for axial only on the project. Well, project we don't have. We're not having you do this project. Axial load only. Okay. But you can kind of see that one of these 3 would be axial or out of axial load only. If we had out of plane bending, we're going to start having, when we add in bending loads, that means we're going to have the W loads here, right? So have all 3 of these, or all 4 of these. We haven't done live with roof plus snow or any of those, so we've been mainly doing the first 3. 6 controls for combined bending, right? So 1, 2, 3, 4, 6 is this one. This is if we had live, wind, snow, the whole works. All right, so don't get too confused here. Forgot to take that project piece off, but essentially, if we start adding in wind load, for instance, just wind, this one is going to control. So if I have dead load and just a lateral load, that guy's going to control. If I have a lateral load where I have, sorry, if I have a lateral load with combined with some of these other loads, I'm going to have this guy here, right? 0.75 live, 0.75, 0.6 wind. All right. So you'll know, I'll tell you what loads we're looking at and might give you a heads up to be careful if you've got one of these cases, just so you remember that there are factors in those. All right, so that's kind of the overview of combined bending and axial, and we will do some example problems next.